Welcome to clickmyproject.com. Image sharpness assessment based on local phase coherence. Quality assessment of visual images is of fundamental importance in modern multimedia systems, where various types of distortion are introduced during acquisition, storage, transmission, processing, and display of images. Sharpness is an important determinant in visual assessment of image quality. Existing blur sharpness evaluation algorithms are mostly based on edge with local gradient or energy reduction of global or local high frequency content. In this paper we are concerned about NR assessment of image sharpness, which is one of the most determining factor in human judgment of image quality. Sharpness is closely associated with blur, which is the most common type of distortion that impairs visual sharpness. In practice, blur may occur during the image acquisition, for example due to the atmospheric turbulence, camera motion, or out of focus of the optical system. It may also be a side effect of certain image processing operations such as compression and denoising. Interestingly, the human visual system has a remarkable capability to detect image blur without seeing the original image, but the underlying mechanisms are not well understood. We propose a flexible framework that allows for LPC computation in arbitrary fractional scales. We then develop a new sharpness assessment algorithm without referencing the original image. We use 4 subject-rated publicly available image databases to test the proposed algorithm, which demonstrate their competitive performance when compared with state-of-the-art algorithms. The flow consists of 5 modules: pre-processing, LPC evaluation, sharpness estimation, and performance evaluation. In load image processing, we will load the input test image, which is to be estimated as a sharpness. In the second model, local phase coherence, we closely examine the phase patterns at shape features. We analyze the LPC relationship in 1D, and the results can be directly extended to the 2 dimension. In LPC evaluation algorithm, we can quantify the strength of LPC by assessing the closeness between the true phases of this coefficient and their optimal model predictions. We eliminate both the wraparound effect and the ambiguity between different features. We pick a set of samples at a specific position and scales in the scale space so that the LPC computation can be largely simplified. The next block is sharpness estimated. Input image whose sharpness is to be evaluated is allowed to pass through a series of n-scale M orientation lag Gabor filters without any subsequent downsampling process. In order to provide an overall evaluation about the sharpness of the test image, we need to pool the LPC map into a single sharpness index. An effect in subjective sharpness assessment is that humans tend to make their judgment based on the sharpest region in the image. The last block is performance evaluation. We test the performance of the proposed sharpness measure using 4 blur data sets obtained 4 independent publicly available images databases. We calculate the peak signal to noise ratio and the mean square error values for the original and blurred image after the application of this algorithm. We compare the proposed LPCSA method against 7 existing NR sharpness measures. One useful feature of the proposed LPCSA approach is that it provides an LPC map that indicates the spatial variations of the local sharpness. Run main guide.m file. A new guide window is appeared. These are the push buttons and these are the axes to display the images. Initially, I load the test image by pressing this push button. Select the database from the database. Select any one of the images from this gallery. The input image is displayed in the first axis. Then I apply the gray conversion for this input image. Then I apply the blurring for this input image. This is the blurred output, and I apply the local phase coherence for the original image. The output is displayed here in this axis. These are the feature values displayed in this UI table, and I apply the LPC for the blurred image by pressing this push button. This is the LPC for blurred image. For blurred image, the output is not perfectly, and then I press the performance evaluation to calculate the mean square error and the peak signal to noise ratio, and then press calculate push button. These are the original image mean square error value, that is 0.11, and the original image PSNR value is 57. For blurred image mean square error is 0.12 and PSNR is 57.1886. From this I conclude that we propose an LPC based method for the assessment of perceived image sharpness without referencing the original image. The underlying assumption is that blur affects the LPC relationship. Near sharp image features and the degradation of the LPC strength can be employed to measure image sharpness. We derive a flexible framework to evaluate the LPC strength in arbitrary fractional scales. We propose an efficient algorithm that largely simplifies the LPC computation, making it easily applicable in practical application. We then develop a novel LPCSA image sharpness method which shows the competitive performance when compared with the state-of-art algorithm. These promising results inspire us to extend the current work to other image processing applications where LPC may be employed as a new type of prior model of sharp natural images. Thank you.